Hello, and welcome to this last video on Chapter 19 of Young and Freedman's University Physics. This is a chapter on the first law of thermodynamics, basically that energy is conservation of energy. And this section is on adiabatic processes for an ideal gas. What in the world is that about, you ask? I'm not sure. Well, let's find out. So first of all, what is an adiabatic process? 2 videos ago, we defined an adiabatic process. And an adiabatic process is a thermodynamic process in which no heat transfer takes place between a system and its surroundings. So maybe we have a very carefully insulated situation here to where the system is so well in. Now, of course, this can never be done perfectly. It's going to always be on an absolute level a imprecise kind of thing, but we can approach it for us big people in the macro world. And so if you have a really good insulation, or if it happens so fast that there's not much time for heat exchange, like for example, when you pop a cork and the gases expand so rapidly that there's not much chance for there to be much heat exchange. And when this happens, you'll notice that there's always kind of a vapor around the bottle top, the top of the bottle, because the rapid expansion of the volume has caused a drop in temperature. And as we're going to see, if I ever stop talking, that's going to happen, especially for an ideal gas. You're going to have, if you have a rapid expansion to where there's no time for heat exchange, you're going to have a rapid decline in the temperature. Okay, let's move in. So with an adiabatic process, there's no heat exchange. Q equals 0, which means that in the what is the formula for the first law of thermodynamics? Well, one version is delta U, the change in internal energy, equals Q minus W. That is the heat exchange minus the work done on the any work done on the surroundings. And so if Q is 0, then it's going to basically reduce to delta U equals negative W. Now, for an ideal gas, an adiabat, what's an adiabat? It's not an acrobat. Those are fun too. But an adiabat is the graph, and it's actually behind me, poorly driven, but I'm not violating any copyright laws because I drew that. Anyway, it's not on the wall, it's fake. But anyway, so an adiabat is a curve showing on a PV diagram. I'll just show you one. Here it is. So an adiabat is the curve of basically the relationship between the pressure and volume. See, this is a PV diagram. P stands for pressure. That's good enough for me. V stands for volume. That's good enough for me. Okay, so these lines here are what are called isotherms because they are at a constant temperature. An adiabat is not at a constant temperature. And so what we find is that the relationship between the pressure and volume, that curve, the curve of an adiabat, is going to be steeper than the curve of the isotherm it hits at any particular point. So going back, for an ideal gas, an adiabat is always steeper than an isotherm going through the same point. Okay, it's kind of like an acrobat. Yeah, whee. Okay, let's move on. It's a very steep slide. That'd be fun, maybe, as long as there's like something soft to land in. Okay, so work. I thought I'd start more or less where this section ends. There's a lot of math in this section. Nobody told me there'd be math in physics. Well, okay, I did. But I wanted to kind of start where this section ends in what I take to be the most important formulae to take away from this. And if you look at the summary in this chapter, these are these three formula of, anyway, adiabatic curves are, these 3 formulas seem to be the most important equations to take away from this chapter. I'm going to do it all, don't worry. So for an ideal gas, we remember that the change in internal energy is going to equal the number of moles times the molar heat constant there at a constant volume, molar heat capacity at constant volume times T2 minus T1. So that's from a previous section in the chapter for an ideal gas. Now, in an adiabatic process, Q equals 0, and delta U, change in internal energy, equals negative W. So we can say that the work done, so I've just changed the sign of it, is going to equal this. But because we've changed the sign, we've got to flip the T1 and the T2. That's where the negative went. You might have said, I thought it was, so negative W equals this. So W equals this with the signs of these flipped because we've negativized them. Okay, so here's our first formula that I think is one of the main takeaways from this section. That the work done in an adiabatic process is the number of moles that we're talking about times the molar heat capacity at constant volume. That's a constant, right? You can look it up. Times the beginning temperature minus the final temperature. And so that will tell you the total amount of work done for an ideal gas in an adiabatic process. That, I think, and the number one thing to take away from this section is this formula right here. But that formula leads to a couple other formulae. You say formulae, I say formulae. That's the Latin, formulas. Okay, so we started with this, right? Oh, that V is annoying me because it's supposed to be a subscript. So give me a second. There we go. Doesn't that look much better? The V is where it's supposed to be. So this is the formula we've just shown from the previous slide. If that's true, then we know that PV equals nRT, right? So N equals PV divided by RT, right? And so if we go ahead and do that, and I'm sorry I didn't put it out, here's what we end up with. So the CV stays the same. We've substituted PV, okay, over RT, so the R stays in the bottom, and the PV stays at the top, and the T goes away. And so we have P1V1 minus P2V2. So how did we get from here to here? We simply substituted PV over RT for N, and then canceled. Okay, so here's the second formula that I think is the most important thing to take away from this section. And basically, it expresses the work done in an adiabatic process in terms of pressure and volume as opposed to temperature. So this formula expresses work done in terms of temperature, and this formula expresses work done in terms of pressure and volume. Now, there is you might remember the constant that was introduced in the previous section called the ratio of heat capacities, gamma. And so gamma was the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. That's what gamma is. And so if we substitute in for gamma, in other words, CV equals in relation to gamma, this is how it ends up. This is the same, but let me footnote, okay? So if gamma equals this, then we can find what CV is in terms of gamma, you know, and substitute it in for CV, and this is what we end up with. But just to remind you how to do that. So R over CV, remember we have CV over R, so this is basically the inverse of what we had there. So R equals the, oh, it's still large. 1 second, please. Sometimes when I cut and paste these formulas, the subheadings disappear. It's all right now. So the gas constant over the molar heat capacity at constant volume, well, R, we know from a previous section, is the molar heat capacity at constant pressure minus the molar heat capacity at constant volume, right? And so we've substituted in for R. Well, this is simply Cp over Cv minus Cv over Cv, which is minus 1. And since this is gamma, we know that this is gamma minus 1, right? And so since it's flipped, blah, blah, blah. So since it's flipped, there we are. Since this is CV over R as opposed to R over CV, we just flip it. 1 over gamma minus 1 times this. So anyway, this is just simple algebra and substitution, blah, blah, blah. And so here you have it. The trinity of work formulas from this section that express the work of an adiabatic process in terms of temperature, the work of an adiabatic process in terms of pressure and volume, and the work of an adiabatic process in terms of gamma. Okay, Ta-da! So this is what I take to be the heart of what you need to take away from this section. However, there's a lot more. This video will now go on for some time. Okay, and I've already defined gamma as the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. Okay, so, and now more. Okay, so we've got this formula, right, from a previous, how do we get to this formula? That's what I'm going to now show you. How do we get to this first formula? So what you need to know is the formula. How did they get this formula? Well, let's go. We know that for an ideal gas, remember this was one of the things we've learned in this chapter, that the change in internal energy of an ideal gas depends solely on temperature, not on pressure, not on volume, but the change in internal energy of an ideal gas depends solely on temperature. And here's the formula from previously on first law of thermodynamics. Okay, so we also know that dW equals PdV, work equals pressure times volume, right? So now that means we also know that for an adiabatic process, the heat exchange is 0. So put it all together and we get that du, which is this, equals negative dW, which is this, right? Okay, so we've simply taken what we know about adiabatic processes for ideal gases, and we have arrived at this formula right there. Okay, so let's keep going. Oh, let me make it suspenseful. So let's do the same thing we did. Let's substitute in for P. PV equals nRT, right? So P equals nRT divided by V, right? So we just substitute in this for P, right? And now we've got some stuff that we can shuffle around. So if we bring the T on this side, then we have dT, the infinitesimal change in temperature divided by the temperature. And if we pull this on this side, it becomes positive. R over V, we shuffle around a little, and we've got R over CV, and because we brought this on this side, and we already had the dV there, so we had dV over V, still have it, and we still have the R, and we brought the CV on this side, and we canceled out the N on both sides, and we now have this expression. The infinitesimal change in temperature divided by the temperature, in Kelvin, by the way, it has to be in Kelvin, plus the gas constant divided by the molar heat capacity at constant volume, times the infinitesimal change in volume divided by the volume equals 0, okay? Isn't it amazing how you can use math to determine things about the world? It's just fascinating to me. It blows my mind. I can't fathom it. Anyway, the madness continues. I already went through that. And so dt over t plus, we had this, right? I already had that. So now if I factor this in, because remember, I can substitute in for CV, R over CV, I can substitute in gamma minus 1 for this, and now I've got a nice little equation here that the infinitesimal change in temperature divided by temperature plus this, which is this equals this, so this equals this, times that, infinitesimal change in volume over volume equals 0. Yep, okay. What are the implications of this formula? Well, one of the implications, so gamma minus 1 is always going to be greater than 1, okay? Because the molar heat capacity at constant pressure is always greater than the molar heat capacity at constant volume for an ideal gas. And so this is always going to be greater than 1. What that means is that in order for these to cancel out, they have to be inverse. So as I said, gamma is always greater than 1 for an ideal gas, or for any gas actually. So dt and dV always have to have opposite signs. If the temperature goes up, the volume goes down. If the volume goes up, the temperature goes down. Adiabatic expansion, therefore, volume going up, must mean a loss of temperature, which is why you get that vapor around, say, a champagne bottle if you take the cork off. And by the same meaning, adiabatic compression is in a piston, where it happens very quickly, is going to mean a temperature gain, which is why gasoline engines work. Okay, so these are the implications of this nice little formula. Implications in the real world of a bunch of little letters and squigglies. Okay, now if we integrate both sides of this equation, so here's the equation. If I integrate both sides, and again, this is a formula that you may have forgotten from calculus, or maybe you haven't gotten there yet in calculus, so you're getting a little preview. But basically, if you integrate both sides, the integral of dt over t, the integral of dx over x is going to be the natural logarithm of t or x, and whatever it is you're doing. So same thing over here. If you integrate this, it's going to end up this, and this is a constant, so it stays the same. And how do you get, so the integration of 0 is going to be a constant, because if you take the derivative of a constant, you get 0. And so when you're integrating from 0, you get a constant. Remember, the fundamental theorem of calculus, they're inversely related. Okay, so this is what happens when we integrate both sides. We still have an equality. Now, we can then play with some of the rules of natural logarithms. So one of the rules of natural logarithms is that if you have something out front, that it's the same as the natural logarithm of that thing raised to that power. Okay, so you can do this. It's part of the definition of the basic rules of natural logarithms. So natural logarithm of t plus another natural logarithm of v to the gamma minus 1 equals a constant. Okay, another rule is if you have two logarithms that are added to each other, it's the same as taking the logarithm of those two things multiplied by each other. So I can bring these two together, multiplied by each other. The natural logarithm of temperature times volume raised to the gamma minus 1 equals a constant. And in that, it's just fascinating to me that the real world corresponds to math. Okay, so if I then take e to both sides, so e to the natural logarithm of this, it cancels out. Like if you're doing the string thing, it just, it's gone. And so if you take e to the natural logarithm, it gets this. And then, of course, e to a constant is another constant. And so basically, we have this formula, which is another one of the takeaways, I think, of this section. Okay, and by the way, if this equals a constant, then we know that this is a linear equation, which means that any set of temperature and volumes are going to be proportional to each other. So we can now say for an ideal gas that is undergoing a adiabatic process, that temperature 1 times volume 1 raised to the gamma minus 1 is going to equal temperature 2 times volume 2 raised to the gamma minus 1. So again, these are some of the little takeaways from this section, in addition to the 3 formulas we started with. Okay, so now we've got a nice little truth about the temperature and volume relationships of a adiabatic process of an ideal gas. What about pressure and volume, you ask? I know you were asking. So we started again with this. Okay, we know that T equals PV over NR. It's the old PV equals NRT. So we plug that in for T, and what do we get? We get that PV over NR times V, I just substituted in for T, equals a constant, right? Which, well, N is the number of moles, that's going to stay constant. R is the gas constant, that's going to stay constant. So we got a constant over here. So if we multiply both sides by NR, we get PV to the gamma equals another constant. We don't know what the constant is, but we know it's a constant thing. Where did I get, where did I lose the 1? Well, volume times volume to the gamma minus 1 equals volume to the gamma, right? Because I've multiplied, this is 1 plus, when you multiply, you add the exponents, right? So volume is to the power of 1. So if you multiply these two V's together, you get V to the gamma minus 1 plus 1, which is volume to the gamma. So that's how we ended up with this. But if that's the case, then we have a linear relationship, right? And so we know that pressure 1 times volume 1 to the gamma equals pressure 2 times volume 2 to the gamma for an ideal gas in an adiabatic process. Ta-da! So this is another useful relationship to know about adiabatic processes. Okay, well, hey, I've run out of video, finally. This is a long video, a lot of math in this particular section. But despite all that, so what are your takeaways? I should have had a final, let me have a final slide for this one. Why do it verbally when I can show you? So here are what I take to be the main takeaways from this section. First of all, the three work equations. This is the biggest thing to take away because it's in the summary. So this is the work, oh, and it didn't do the V again. Okay, so the three work equations. This expresses the work done during an adiabatic process. You can see it in the shaded area behind me, under the curve there between the 2 points. The work done in an adiabatic process in terms of temperature, the work done in terms of pressure and volume, and then that same expression, but we've changed this into the gamma molar heat ratio. Okay, so that was the big thing to take away from this chapter. Also, you should take away that in an adiabatic process, temperature and volume are inverse. If the temperature goes up, the volume must go down. If the volume goes, or if the volume goes up, the temperature must go down. If the volume goes down, the temperature must go up. So they're inverse. And then lastly, there were these two relationships between temperature and volume and pressure and volume in an adiabatic process. That's a summary of this very long video. Well, this is the end of this chapter. Yay! On to the second law of thermodynamics.